Today we're going to go over the Chapter 15 Comprehension Check. Now, Chapter 15 starts off our study of kinetics. And for this chapter, you're going to need to remember what we've learned about concentration and molarity. And we're going to apply that to what we call kinetics. And kinetics is the study of a chemical's reaction rates. Now, just how if you're going somewhere in a car, the rate of your travel would be your distance divided by your time. We have rates for how chemical reactions happen. Now, when we measure the rate for a chemical reaction, we're not measuring distance because the reaction isn't like traveling a distance, but what we're measuring is concentration. And so as a reaction proceeds, the concentration of the products, so in this equation, your concentrations of A and B will be going down, and you'll see the concentrations of, so you'll see as a reaction goes on, instead of covering distance, what will happen is you're going to see the concentration of your reactants go down and the concentration of your products will be going up. And so we are going to calculate the rate of reactions. Instead of being distance over time, we calculate it with concentration over time. So now if we're using this equation as our basis for it, we have two ways of calculating the rate of a reaction. And so I've got the line for the two parts, but this part uses C, which is a product. And as a reaction goes on over time, the product of a reaction should be increasing. And so this is just a positive number, and the rate is in that positive direction. But let's say you don't know the concentration of a product to try to calculate the rate of a reaction. And instead, they give you the concentration of the reactant. So it's kind of like we're working backwards, and we've done this a lot in this class. But if I know the concentration of the reactant that I have at this current time in the reaction, I can calculate the rate. The only thing that is different in this is the sign changes for if you're using the reactant instead of using the product. And so when you see these rate equations, you're going to see this triangle, which we have seen again before, which means delta or difference in. The other thing is you see a little c and it is in brackets. And what those brackets mean in chemistry is concentration. So anytime you see something in brackets, you're looking for a concentration in molarity. And so the concentration of C would be some molarity of this product here. To also calculate the rate of a reaction, you need to know the time. What time has this happened over? Just like in a car, as you're traveling a distance, you have miles per hour. It's the miles you go in an hour. We actually calculate rate the same way, except usually our reactions don't happen in hours. They're going to happen in seconds. So you're going to have a time as a second. So just to give you like a clue as to how these start, I'm going to jump in with comprehension check question number 1. It tells us that this is a study of kinetics, so that's I know I'm going to be doing reaction rates. And then it tells me the concentration of one substance is 1.15 molarity at t or z equals 0 seconds. So this is like before the reaction has even started. And then after 15 seconds, the concentration of this has actually gone down to 0.98 molarity or moles per liter. And so the question is asking me, is this substance a reactant or a product, and what is the reactant rate? Well, like we said a minute ago, in order to calculate the reactant rate, we need to know if it's a product or a reactant, because it depends on the sign that we use for the reaction rate equation. Now, a reactant is going to be going down, right? It's getting consumed during the reaction. And as the reaction proceeds, the products are going up. So in this reaction, I know that I'm going from 1.15 molarity down to 0.98. So that tells me that this is a reactant. Now, since I know that this is a reactant, I can use the rate equation for a reactant. And so that is going to be this rate equation with a negative in the beginning. And just like I have above, I've rewritten the equation for the difference of the concentration. So the sign, right now we're not using that, we'll use that in a minute, but the delta A is the difference in concentration, and I'm going to be dividing it by the difference in time. So to calculate the difference in concentration, just like when in the past we've calculated like delta T, you're going to be taking the final concentration and you subtract the initial concentration. So it would be like 0.98 minus 1.15. And you get a negative 0.17 molarity. It's negative because concentration is going down here. The difference in time is going to be 15 seconds minus the initial time, which is 0, so it's just 15 seconds. So now we have a negative times a negative, so these are going to clearly cancel out, and you're going to have an answer as a positive, and you're going to do 0.17 divided by 15. That is an S, not a 5. And we calculate a rate for this reaction as being 0.011 moles per second, or molarity per second, which is basically like every second, that's the change of the concentration that is happening per second of this reaction. And so when we have reaction rates, the reaction rates are always going to be positive, and that's kind of the purpose of this negative here, is to make sure that you get a positive reaction rate. So as we practice these reaction rates, we're going to look and see if there's a few things that can affect a reaction rate. And you may actually do some of these in lab, or you actually may be able to just logically think through these. And so question number 2 gives you, there's 3 parts, A, B, and C, and each section gives you like 2 scenarios, and it asks you to pick which one would have the slowest reaction rate. And it asks you to pick what is the slowest reaction rate. So for the first part, it says you have a large chunk of a solid that you're reacting, or you have the same mass, it's just powdered. And so this does affect the reaction rate with something we call surface area. So you may do this experiment in class, or something really similar to where you have a cup of vinegar and you take a Tums and you just drop the solid Tums or antacid into the vinegar. And then you also are going to do it again as you powder it up and you crush it up, and then you put it into it. And what happens is, as you're grinding up a compound into a powder, you're actually making more surface area, and more surface area is just more places where the reaction can be happening. So the more surface area you have, the higher the reaction, or the faster the reaction is going to proceed. And so the question wants you to underline or like note which ones would go the slowest. And so that would be the large chunk of the solid would be a lot slower reaction. So for part B, we have one reaction that we're doing, and we're doing it at 15 degrees Celsius, or we're doing it 50 degrees Celsius. And as you know, as you heat things up, they get moving around more, and the more molecules are moving around, the more they have collisions and can actually have reactions. And so a lower temperature is going to have a slower reaction rate. Question number C is an acid-base reaction, and it tells you the first part you have a 5 molar of the base, and in the second part you have a 1 molarity solution of the base. And I think that we talked about concentrations, but the higher the concentration is, the faster this reaction is going to go, because the more of an acid or the more of a base you have in your reaction, the more chance you have for interactions and collisions, and so the faster that reaction is going to happen. So this is going to be your slower reaction. As you start to study chemical reactions and kinetics, it is really good to be able to try to predict the rate at which a reaction will happen, and you may test different concentrations to try to figure this out, because there are times when you want a reaction to proceed really fast. And an example of that would be in the airbag of a car. You want an airbag of a car to inflate extremely rapidly, so you want it to have a very high reaction rate. But then there are some reactions that we actually want to happen slow over a long period of time. Some of those reactions we have are like long release medicines, that you want to be able to take a medicine and you want to have that reaction be a slow one, so that medicine has an effect over a couple hours of a period of time in your body. And so chemists will try different concentrations out, and they will predict the reaction rate. Now you can do this in an experiment form in the lab, where you do a reaction and you time it, or you can do this by calculations. So we're going to learn how to do a calculations of this. You're going to get a new equation. I know we've had so many equations this year, but you're almost done with them. But so you have seen me write an equation this way before. These are just my kids' magnets, where we have the little a and the big A. And the little a is just the moles, comes from the balanced chemical equation, and the big A just represents the reactant. The other is we have the actual equation or the math equation. For this, the rate, we say the rate is equal to K, which K is a constant, and you're going to see a table in your textbook where you can simply look up that table. And then you have the concentration of A, and it's raised to a power, and I'm going to talk to you about that in a minute. And then you have the concentration of B, and it's raised to a power. We're calculating these rates based on the concentration of the reactants that I'm starting this experiment with. Now, the K, the constant, you're going to have a table that you look up. Now, these constants are a little bit confusing compared to some of the others because the constants can change. The K will be different for different types of reactions and for different temperatures. So as you look on some of these charts, make sure you're noting that they're at different temperatures or they're in different reactions. The other part of this that you're going to see is you're going to see an X and a Y. And so these are something that we don't really dig too much into this class, but that is called the order of the reactants. And you're going to see an order of reactants. You're going to see either a 1, a 2, I think we may even see a 0 in here. And if we put the 1 in front of 1, it means this reaction is dependent primarily on the concentration of this reactant. So that would be like the first order, means that the concentration of that reactant is what affects the rate of the equation. And if you put a 2 in there for a second rate, it kind of tells me that as the reaction proceeds, that reactant is consumed as the product goes on. Question number 3 gives you a situation. It tells me we have a reaction that has 2 reactants. And then, like I just said, it tells you your order, which is these exponents. So it says the first reactant, it is a 1. So it would be something like this, and you would have a little 1 there. There's some constant K here, and this is the rate. And then it tells me that the overall order of the whole thing is a 1, and it's wanting me to calculate the order of the second reactant, which is this Y here, which would be Y here. Now, when we're determining what we call the overall order of a reaction, try to think about math when you have exponents and you're multiplying by exponents, you actually add the exponents. So this reactant is what we call first order. And this reactant, we don't know what its order is. And I understand that orders are really complicated, especially because this book does not really explain it. It wants to know what the order for the second reactant is. So if I say this is a 1 and I have Y and the total order is a 1, I know then that this must be a 0 because 1 plus 0 would equal 1. If you're confused on that, it's okay. Part B wants us to determine the unit for the rate constant. Now, rate constants are they can change, like I said earlier, based on the temperature or the reaction. But in addition to that, the units of a rate constant can change. So if I put something in here and it's raised to the power of 0, from algebra, you should know anything raised to the power of 0 is just a 1. So I'm going to just get rid of this. And so now let's see if we can try to figure out what the units of this must be. Now, a rate we talked about is in concentration, which is a molarity, over seconds or time. And this is a molarity. Now I'm trying to find the units for K, so I'm just going to divide both of these by M. All right, now this may look a little weird, so I'm going to move it over here. So if you have an M over an S divided by an M, right? Division of fractions, you're going to multiply by the reciprocal. M's cancel out, and your unit is 1 over S. So your constant for this is per second, or 1 over second. Now, why do we do that problem? Just to show you that the unit for the constant here can be different, because if we had another concentration here, we would have a different unit. So this is a different constant than any of the other constants we've used so far in this book. For question number 4, they give you a reaction of nitrogen monoxide and O3, which is ozone. And they give you also a chart to use for this equation. And they ask you to figure out the rate equation for this. So we're just going to start with this basic equation. And I'm going to use the concentration of my reactants. Now for the overall reaction, they don't give me the K or the constants for that. And so I'm actually going to have to go through and do a bit of calculations. So on the problem, you're going to see, and I'll add the chart up above, you're going to see 3 trials. So they've essentially done this reaction 3 different times. And so we're going to actually have to pick some of these trials and analyze it. So what we're going to do is we're going to pick 2 trials where one of the reactions stays the same. And we're going to see what happens in the 2 trials or compare the 2 trials to each other. So if you look at trial 1 and trial 2, trial 1 has the same concentration of NO, and then they change the concentration of ozone in each of the trials. So what we're going to do so that we can try to get this ratio or try to figure out how these relate to each other is I'm going to write the rate equation for trial 1 and trial 2. So let's do trial 1 first. Now, the rate, it actually gives you in the chart, they call it the instantaneous rate, but it's there. And so for trial 1, it's 22.0. I put everything in for trial 1, and I'm not going to put anything for the orders. I don't know anything about that right now, so I'm not going to worry about that. But I'm just going to write these equations so that maybe I can compare trial 1 to trial 2. So trial 1 is 22 is the instantaneous rate on it, and they give me when I fill in the concentration. So let's do that same thing for trial 2. And trial 2 is actually 44. And the concentration of NO stays the same throughout this trial. That's how I can compare. I'm basically comparing when this concentration of ozone changes, what happens to the rate. And so if I did trial 2, it's got a 44 milliliters per second is its rate. I don't know K. The concentration of NO stays the same. And what's happening is I'm having a change of concentration of the ozone. Basically what I'm looking for here is like a ratio or a comparison. So since I'm going to try to write a ratio for this, it would be better if I had the equation that had the biggest number on the top. I wish I would have thought that through. So what I'm going to do here is I'm going to move trial 2 to above here. So it's like 44. And it's kind of like I'm setting it, I'm dividing it by it. For my ratio, the first part is trial 2 and trial 1. The reason I put trial 2 on top, in case you didn't remember what I just said, it's because it's a bigger number and I don't want to end up with a decimal point. I want to end up with a nice whole number. So we're trying to get a ratio basically of how these react. So if this was division, these would cancel out because they are the same. I made a mistake. This is not 1. This is a 2 for trial 2. These units are going to cancel out. The K's are going to cancel out. And I am left with this basically if I cancel out the M's. And this is a concentration raised to some order if we're keeping our units the same. Now, I could actually go through here and take and set it up this way. Just basically simplifying it through more and more. And so for here, actually 44 divided by 22 works really nicely. It is 2. So now, if you were going to take this and you ran it through your calculator, you would then end up with 2, and this simplifies out to being 2 equals 2.0 raised to some y that we don't know. Now, the only way that this equation could actually work is if y is 1. So now I know in my rate equation that y is 1. All of that to figure out that. But now I have to do something very similar to figure out what the value for x is. To find out what x is, I need to set up a rate equation so that y cancels out. I hope you remember from algebra when you add equations, if you have two unknowns, right? I need to get rid of the y's in the equation so that I'm left with only x. So that when I write this equation, I also know what x is. Now, x is the equation that is next to the reactant A, or NO in this case. And Y is the one that is next to the oxygen. So I want to find two trials that oxygen is the same. That way when I do the math, I can cancel out the oxygens. And so for this problem, that would be trials 1 and trial 3. If you look on the chart, you'll see oxygen in both of those trials. I'm gonna write trial 3 first, because it has the bigger number and I want the bigger number on top. I don't want to have to rewrite it like I did in the last problem. I'm doing trial 3. This information is just coming from that table that they give me with the problem, where I have the instantaneous rate, then I have the concentration of nitrous oxide, and I have the concentration of ozone. So I'm going to do it now. I said I was going to compare trial 1 to trial 3. Well, we just did trial 1. If I write trial 1 below it, once again, I'm trying to find this ratio, or I'm trying to calculate what x is. So I'm going to do it this way like I did the last time. Set my larger one on top of the smaller one. That way when I do division, I get a good clean number. Let's see what all cancels out. Constants cancel out. This whole thing's going to cancel out. So if I rewrote this, 44 divided by 22 is 2. So when I mark cancel out, I'm going to end up with, I'm basically canceling out all my units, all but this 0.002 and this 0.001. And these are still raised to a power of x. Don't know what that is. That's what I'm solving for. You do 0.002 divided by 0.001, you get 2. So I know I have 2 equals 2 raised to some number. And the only way that this would be possible is if x was 1. I now know not only was y 1, but x is also 1. So with x and a y value, I can figure out the rate equation. So the rate equation is the constant times the concentration of NO raised to the power of 1, because we figured out those are all powers of 1, times the concentration of ozone raised to the power of 1. The second part of this equation is they actually ask you to figure out K for this equation. So there's lots of parts. We just did all that work to find these two tiny little ones, and now we're going to figure out K. To figure out the constant for this whole reaction, you can pick the information from any of the trials and put in for the rate and the concentrations to solve for K. It's your choice as to which trial you do. I'm going to choose trial 1 because the first one, because we've worked with it so much already. So when I put in the information for 1, I know the rate is 22 molarity per second. I'm still solving for K. I dropped these 1 exponents because they don't actually matter for the algebra of it. And I'm basically put in the concentration. So I am going to rework this formula so that I can solve for K. I'm going to do that by dividing both sides by these numbers. And you can put this in your calculator in one motion. That, like normal, helps prevent rounding errors. And you're also going to pay close attention to your units and how they work out. In the numbers, you get 2.2 times 10 to the 7th. For units, let's see what we calculate, because the units are not the same for every constant for these guys. We have molarity over seconds, and we're dividing it by molarity squared. So when I'm dividing, I'm going to be multiplying by the reciprocal. And so I have 1 over seconds times the molarity. And that's going to be your units for the K constant for this reaction.